Inverses and radical functions. In this section, we will explore the inverses of polynomial and rational functions, and in particular, the radical functions that arise in the process. Example 1. A water runoff collector is built in the shape of a parabolic trough as shown below. Find the surface area of the water in the trough as a function of the depth of the water. Since it will be helpful to have an equation for the parabolic cross-sectional shape, we will impose a coordinate system at the cross-section, with x measured horizontally and y measured vertically, with the origin at the vertex of the parabola. From this, we find an equation for the parabolic shape. Since we place the origin at the vertex of the parabola, we know the equation will have the form y of x equals ax squared. Our equation will need to pass through the point 618, from which we can solve for the stretch factor a. 18 equals a6 squared. A equals 18 divided by 36 equals half. Our parabolic cross-section has equation y of x equals half x squared. Since we are interested in the surface area of the water, we are interested in determining the width at the top of the water as a function of the water depth. For any depth y, the width will be given by 2x. So we need to solve the equation above for x. However, notice that the original function is not one-to-one, and indeed, given any output, there are two inputs that produce the same output, one positive and one negative. To find an inverse, we can restrict our original function to a limited domain on which it is one-to-one. In this case, it makes sense to restrict ourselves to positive x values. On this domain, we can find an inverse by solving for the input variable. Y equals half x squared, 2y equals x squared, x equals plus or minus the square root of 2y. This is not a function as written. Since we are limiting ourselves to positive x values, we eliminate the negative solution, giving us the inverse function we're looking for. X of y equals square root of 2y. Since x measures from the center out, the entire width of the water at the top will be 2x. Since the trough is 3 feet, 36 inches long, the surface area will then be 36 multiplied by 2x, or in terms of y, area equals 72x equals 72 multiplied by the square root of 2y. The previous example illustrated two important things. One, when finding the inverse of a quadratic, we have to limit ourselves to a domain on which the function is one-to-one. Two, the inverse of a quadratic function is a square root function. Both are toolkit functions and different types of power functions. Functions involving roots are often called radical functions. Example 2. Find the inverse of f of x equals x minus 2 squared minus 3 equals x squared minus 4x plus 1. From the transformation form of the function, we can see this is a transformed quadratic with vertex at 2, -3 that opens upwards. Since the graph will be decreasing on one side of the vertex and increasing on the other side, we can restrict this function to a domain on which it will be one-to-one by limiting the domain to x greater than or equal to 2. To find the inverse, we will use the vertex form of the quadratic. We start by replacing the f of x with a simple variable y, then solve for x. Of course, as written, this is not a function. Since we restricted our original function to a domain of x greater than or equal to 2, the outputs of the inverse should be the same, telling us to utilize the positive case. X equals f inverse of y equals 2 plus square root of y plus 3. If the quadratic had not been given in vertex form, rewriting it into vertex form is probably the best approach. Alternatively, we could have taken the standard equation and rewritten it equal to 0. 0 equals x squared minus 4x plus 1 minus 1. We would then be able to use the quadratic formula with a equals 1, b equals -4, and c equals 1 minus y, resulting in the same solutions we found above. X equals 2 plus or minus the square root of 3 plus y. Try it now. Find the inverse of the function f of x equals x squared plus 1 on the domain x greater than or equal to 0. While it is not possible to find an inverse of most polynomial functions, some other basic polynomials are invertible. Example 3. Find the inverse of the function f of x equals 5x cubed plus 1. This is a transformation of the basic cubic toolkit function, and based on our knowledge of that function, we know it is 1-to-1. Solving for the inverse by solving for x equals f inverse of y equals the cube root of y minus 1 divided by 5. Notice that this inverse is also a transformation of a power function with a fractional power x to the 1/3 power. Try it now. Which toolkit functions have inverse functions without restricting their domain? Besides being as an inverse function, radical functions are common in important physical models. Example 4. The velocity v in feet per second of a car that slammed on its brakes can be determined based on the length of skid marks that the tires left on the ground. This relationship is given by v of d equals the square root of 2gfd. In this formula, g represents acceleration due to gravity, 32 feet per second squared. D is the length of skid marks in feet, and f is a constant representing the friction of the surface. A car lost control on wet asphalt with a friction coefficient of 0.5. leaving 200-foot skid marks. How fast was the car traveling when it lost control? Using the given values of f equals 0.5 and d equals 200, we can evaluate the given formula. V of 200 equals the square root of 2 multiplied by 32 multiplied by 0.5 multiplied by 200 equals 80 feet per second, which is about 54.5 miles per hour. When radical functions are composed with other functions, determining domain can become more complicated. Example 5. Find the domain of the function f of x equals the square root of x plus 2 multiplied by x minus 3 divided by x minus 1. Since a square root is only defined when the quantity under the radical is non-negative, we need to determine where x plus 2 multiplied by x minus 3 divided by x minus 1 is greater than or equal to 0. A rational function can change signs, change from positive to negative or vice versa at horizontal intercepts and at vertical asymptotes. For this equation, the graph could change signs at x equals -2, 1, and 3. To determine on which intervals the rational expression is positive, we could evaluate the expression at test values or sketch a graph. While both approaches work equally well, for this example, we will use a graph. This function has two horizontal intercepts, both of which exhibit linear behavior where the graph will pass through the intercept. There is one vertical asymptote corresponding to a linear factor, leading to a behavior similar to the basic reciprocal toolkit function. There is a vertical intercept at 0, 6. This graph does not have a horizontal asymptote since the degree of the numerator is larger than the degree of the denominator. From the vertical intercept and horizontal intercept at x equals -2, we can sketch the left side of the graph. From the behavior at the asymptote, we can sketch the right side of the graph. From the graph, we can now tell on which intervals this expression will be non-negative, so the original function f of x will be defined. F of x has domain -2 less than or equal to x less than 1, or x greater than or equal to 3, or in interval notation, -2, 1, union 3 to infinity. Like with finding inverses of quadratic functions, it is sometimes desirable to find the inverse of a rational function, particularly of rational functions that are the ratio of linear functions, such as our concentration examples. Try it now. Find the inverse of the function f of x equals x plus 3 divided by x minus 2.